Okay. Not only can we represent bilinear mapping by matrix representation, we can do the same for symplectic forms as well. However, of course, we need a standard matrix for this symplectic vector space. And of course, notation, of course, I've come across, or seems to be common, is of course by calling that matrix J. Where J, of course, would be all of its main entries would be J naught. Just to properly define the dots. Where, of course, J naught, each of those entries would be the 2 by 2 matrix, in which that 2 by 2 matrix is going to consist of the entries, of course, 1, 0, negative 1, 0, which this, of course, is a skew symmetric matrix, and that corresponds to the standard basis of the symplectic vector space. And of course, by seeing, of course, the transpose, that, of course, is the opposite, the multiplicative inverse of the matrix. Well, for the this matrix representation, of course, corresponds to any particular, of course, symplectic or bilinear function that we have for the bilinear mapping for the symplectic vector space. Of course, this is the standard matrix that must be used in order for transformations and other properties of matrix multiplication to be used. So, if, for instance, and the bilinear, or we had from transformation from R2 then, R2 then, this would be, of course, where T is a linear symplectomorphism. We'll talk about linear symplectomorphisms here in a moment. If T is a linear symplectomorphism, or just abbreviate that word, of the symplectic vector space R2n, and we can use, of course, we'll use phi naught, just introduce some new notation. If this is so, this, of course, is a linear symplectomorphism if the matrix representation, this transformation, we can call that matrix A, where A is, of course, the matrix of this transformation, then, and this is, of course, relative to a standard symplectic basis, and this was matrix. This matrix up here is, of course, its entries represent that standard symplectic basis. This is a linear symplectomorphism if and only if the matrix representation satisfies the following property: that the transpose of this transformation, represented by matrix A, times J, and times matrix A, simplifies to J. Of course, that goes back to, of course, the properties of this that must be satisfied for symplectic vector space, and of course, there being school or thought for this particular vector space. So, what is a linear symplectomorphism? That's pronouncing that word feels as if you had a whole roll of chewing gum in your mouth. I'll say that. So, I'll write this in cursive. A linear symplectomorphism what this is of course, if we have, I'll use this piece of chalk right here, it's starting to fade away. So we have arbitrary vector space V, paired with, of course, some bilinear mapping. Of course, we can use that as phi. And we have a transformation, which is, of course, transformation from vector space V to, of course, itself. This transformation, of course, is an arbitrary statement to this. This is a linear symplectomorphism if, I'll state this, if, of course, for all pairs of vectors U and V, which are, of course, elements, vector space V, phi of transformation of vector U, transformation of vector V is, in fact, simply the transformation phi of vector U to V. And of course, also, otherwise, another way, of course, going back to our pullback functions, this transformation is a linear symplectomorphism if, say we use the pullback of course, pullback of phi by t is equal to phi. Another way to write it. Pretty cool for that connection. So, another thing, of course, that not only can we, going back to our matrix representation, not only can we, of course, still represent our transformations in the symplectic vector space by the use of a matrix corresponding to the transformation, of course, but along with the utilization of a standard matrix for this vector space. The matrix of this transformation, of course, has properties of its own, such as, for this matrix representation, create another section over here, there exists an A inverse, which of course that implies that there exists an inverse transformation. Of course, that's yet to be proven. And of course, these properties can be easily proven, which of course first, I would think that of course the existence of an inverse transformation would need to be proven in order for this to be so. But for the properties, we have that the transpose of the matrix representing the transformation is an element of the set of all, which of course, this is the set of all symplectic matrices. Ditto, of course, is SP2, and of course, 2 indicates, of course, the dimension of the matrix, of course. And A inverse is, of course, an element of the set of all 2n by 2n symplectic matrices. And by knowing this, we can use this for a host of things. And another interesting thing to note is, of course, the matrix representation can go all the way to, of course, finding the eigenvalues of the matrix represented by this transformation, and of course leads to some other cool stuff. Which of course, proving that if lambda is an eigenvalue of an arbitrary 2n by 2n matrix, then so are the eigenvalues 1 over lambda, and of course the conjugate of lambda. Of course, that's a relatively lengthy proof, which goes into, of course, detail, of course, by writing out the characteristic equation by performing operations with the matrices and such. But, however, one final thing I would like to, of course, talk about is ellipsoids. One particular object that is used for measuring of course, the symplectic vector spaces. So, I believe that's the final thing I'll cover for this. These symplectic forms. Uh-oh.
You're on a board.
Uh-oh. Well.
Okay.